Hi, welcome to Game Innovation, a video series dedicated to covering new advancements in game design and technology. Advancements like this, courtesy of NYU. If you're wondering what exactly you just saw, it's what it looks like. A large stone slab of Minecraft blocks that slowly begins to chisel away to reveal an actual complex landscape, effectively creating a small world out of nothing. Which may not seem impressive at first glance, considering Minecraft itself already procedurally generates terrain and has been doing so since 2009. But one thing that's never been part of that process is control. What if we had control? If we could maybe create a crude miniature layout and see it come to life in larger form, or even provide a text prompt to guide the process, similar to text-to-image generators that have become popular recently. Well, that obviously comes with its own set of questions. For example, is that even possible? How is it possible? What do we gain from doing this? And most importantly, is this actually helpful to game developers? With generative AI models coming hand in hand with a laundry list of concerns, particularly in creative fields, can we view this as a simple designer tool that speeds up the creative process, or is it far more dangerous than that? But before we get into that, let's try to answer that first question, to which the short answer is yes. But it's not as simple as generating flat images. To show why, let's look at a popular method for generating AI images, diffusion models. A link to an in-depth explanation of the diffusion process will be posted in the description for those that are curious, but at a high level, this idea is fairly straightforward. You train a model that can turn random noise into an actual image. To accomplish this, you start with what's called a forward process, where you take an initial image and then gradually add noise until the image is completely unrecognizable. At a single pixel level, you might see something like this, where the original RGB values get scrambled over time. Then in training, your model will learn the patterns in the forward process, and will eventually be able to reverse them if given an image with heavy noise. You can also steer it in the right direction with something like a text prompt, giving you the ability to create brand new images that align stylistically with the images you trained on. A key element to note here, though, is that this is all working on continuous data. The information in a pixel, like RGB values and brightness, is effectively on a slider, where pixels with values that are closer together are similar to one another, and values that are farther are dissimilar. This allows us to easily track evolutions and patterns, and measure how close the final result is to the one that we want with some basic math. But in a grid-based world, the individual pieces aren't continuous, they're categorical. You have a stone block, a grass block, a water block, and a sand block, and they're all mutually exclusive, all equally unalike. If you used one hot encoding to represent them, like what's shown here, adding noise to get something scrambled like this doesn't make sense, because there's no part water, part grass, part stone block. So what can we do differently to employ diffusion in grid worlds or other discrete cases? Well, there's a few different options to choose from, but the one we'll be focusing on in this video is Discrete Absorbing Diffusion. Unlike the traditional method of noising pixels over each step, discrete absorption masks pixels during the forward process, slowly replacing pixels with informationless spaces until the entire input has been masked out. The reverse process then unmasks the empty spaces to construct an output based on what the training dataset has taught the model about neighboring pixels or blocks. And this is essentially what we saw in the opening visual. The masked blocks are slowly replaced by information blocks to achieve the desired output. Now, technically, these null blocks wouldn't actually be stone, they would be an inky black void of nothingness. But the core idea is still essentially what's shown here, and the outputs you're seeing are the results of actually testing this diffusion model on a Minecraft grid world. As impressive as that is, however, it's also very computationally expensive. It may not seem like much information, but a 24 by 24 by 24 grid, as shown here, has a total of nearly 14,000 blocks. We discussed earlier how the discrete diffusion process involves unmasking a certain set of blocks at a time to give a final output, and the less blocks we have to unmask at a time, the better the quality of the end result. Which makes the absolute upper limit of steps in this process roughly 14,000. Alternatively, if we had, say, a 6 by 6 by 6 grid of blocks, that upper limit becomes 216, which is 64 times smaller than the previous grid. The only problem being it's also generating 64 times fewer blocks, so the only way this helps us is if we can somehow represent this larger grid as a smaller grid to perform this diffusion. And that's where we get to the second part of this equation, the VQVAE, or Vector Quantized Variational Autoencoder. Once again, a deeper explanation of this model will be linked in the description. As the name suggests, though, this is an encoder that reduces a large grid into a compact size called a latent representation. To do this, it first takes a 4-block wide cube from the larger grid and converts it to a vector representation. For the sake of visualization, we'll show these as 2-dimensional vectors, but in reality they will likely be much larger than that. Now normally, with standard variational autoencoders, we would proceed by doing calculations of means and variance to show how close different vectors are to one another. But in this case, which is working with categorical data, we can actually represent our options as a list of finite possibilities to make them more readable and easy to manipulate. Which brings us to the element of this model that separates it from other autoencoders, a discrete codebook. The codebook is a list of vectors, all with an associated index, that represents a wide range of possibilities in your 4-block wide cube. Let's say index 0 represents a full block of air, index 1 represents a full block of water, index 2 represents half a block of grass, and so on. When encoding a new 4-block wide cube, the vector it gets represented as is compared to all the vectors in the codebook to find which entry is closest to it. And let's say here it's the entry with index 2. You can then represent this entire block with the number 2 in your latent representation, and repeat this process for all of the 4-block wide cubes in your 24-block wide cube to get a 6-block wide latent representation. And because the codebook is designed to be readable by human designers, you could also create your own latent representation using the codebook to produce something completely new. Either way, this can then be diffused using the process we discussed earlier, and then later decoded to its original size. And finally, there's one additional step in the middle that ensures the quality of the output and technically turns this into a VQ-GAN, not a VQ-VAE. And that's it. The full theoretical pipeline for creating Minecraft worlds with diffusion, all while reducing the computational strain of doing so using autoencoders. Now, this pipeline has actually been built out in full by Tim Merino, PhD candidate at NYU's Game Innovation Lab, and a link to this work will be provided in the description. Although one issue that was identified was that by using a single codebook, results were often hard to control and predict. The proposed solution was then to create 2 separate codebooks, one for style, or the type of blocks, and the other for structure, or the arrangement of blocks. Combining the two would give predictable outputs which could also be easily altered by switching one of the codes to a different value. And you can see in this demo how the split codebooks create much more predictable outcomes compared to the old, entangled method. And with this understanding, we can finally get to that last question. How is this all helpful? Because what it seems like is we've just moved closer to text-to-image, but for Minecraft terrain, which means it comes with a lot of the same baggage that text-to-image does. But while it's easy to get immediately stuck on how simple it could now become to generate beautiful Minecraft worlds and even structures with minimal effort, effectively cutting out the talent and passion required to make them, there are also important, helpful, real-world applications of technology like this, especially as we see it evolve further. For instance, it could be used for pre-visualizations, testing of different mechanics under multiple terrain types, and for creating first pass-throughs of levels that can later be altered by human developers. It can also eventually lead to stronger control over procedurally generated worlds, which would be an incredibly welcome technological advancement for developers of roguelikes or massive exploration games like Starfield and No Man's Sky. What's so fascinating about developments like this is that they do make it easier to produce what can be considered soulless products, but they also provide a lot of much-needed assistance to game developers in a time when games are taking longer to make and game budgets are ballooning to unsustainable heights, which is why it's important to understand what these tools are and how they can be used to improve the industry as a whole. And that's what this series is hoping to help people do. So if you enjoyed our quick dive into diffusion and autoencoding for Minecraft terrain, and you want to see more videos on the technological advancements happening in game design, make sure to like the video and subscribe for more. Be on the lookout for the next video, which will release over the next few weeks, and will cover more cutting-edge AI tools for development.